Let's take a look at how probabilities are determined. Now, that just means we're looking at the basics of probability. So we'll also be looking at a little bit of vocabulary and a few fairly simple problems today. If you look at the Common Core State Standards, you'll see that probability is addressed for the first time fairly extensively in 7th grade. Now, it continues to be addressed after that, and after 7th grade, there's also explorations of statistics as well. But 7th grade is really where probability is looked at for the very first time. So here's our first definitions. An experiment is an activity in which the results can be observed and recorded. Now you may think of an experiment like a science experiment, but for us it might be something like flipping a coin or rolling a die. An outcome is a possible result of an experiment. The sample space is a set of all possible outcomes. So let's say we have an experiment, and that experiment is we toss a coin. The possible outcomes for this experiment are that we could either get heads on the coin or we could get tails on the coin, which means the sample space is a set containing those two possible outcomes, heads and tails. And you'll notice notationally we know this is a set because we're using the curly braces to enclose those two elements of the set. Now, because heads and tails have the same probability, they're equally likely to happen when we toss a coin. We call those equally likely outcomes. An event is a subset of a sample space. So let's say our experiment now is to roll a 6-sided die. We could say that one event could be just rolling a 2 on the die. Or maybe an event could be rolling an even number on the die. And if we look at the events that we're defining and we look at the sample space of the experiment, then we can define probability formally. So if an experiment has equally likely outcomes, then the probability of event A is the number of elements in event A divided by the number of elements in the sample space. So let's suppose we have a 10-sided die, and that 10-sided die contains the numbers 1 through 10, and we're going to roll that die once. So that would be our experiment. The possible outcomes would be the numbers 1 through 10, because that's the numbers that are on the sides of the die, and they're equally likely. So if we look at the probability of getting an even number on this die, we could say there's 10 possible outcomes which are equally likely, and the even outcomes are the 2, 4, 6, 8, and 10. So there are 5 outcomes in this event, and there are 10 outcomes in the sample space. So the probability that we roll an even number on this die is 5/10, which of course simplifies to 1/2. If we look at the probability of getting an odd number when we roll the die, we can still say there are 10 elements in the sample space, and there are still 5 elements, the 1, 3, 5, 7, and 9, that are odd numbers. So the probability of rolling an odd number is 5/10, which simplifies to 1/2. Now if you think about those two events, rolling an even number or rolling an odd number, those two events are called mutually exclusive events because they have no elements in common. In fact, the even numbers, the 2, 4, 6, 8, and 10, you can see them circled in red, and the odd numbers, circled in pink, have absolutely no overlap, so they're considered mutually exclusive. Now, if two events are mutually exclusive, then the probability that one of those events happens or the other event happens is equal to the sum of the probabilities of the two events happening separately. Complementary events are mutually exclusive, so they have no elements in common, but together they make up the entire sample space of the experiment. So if you look at what we have in this particular case, the even number and odd number are complementary events. Together they make up the entire sample space, and they are mutually exclusive events. If two events are complementary, then their probabilities will sum to 1. In other words, 1 is the probability of the entire sample space. So let's look at this same 10-sided die. Think about the probability that when we roll this die we get a number greater than 7. There's still 10 elements in the sample space. They are equally likely outcomes. If we look for the numbers that are greater than 7, that would be the 8, the 9, and the 10. So the probability that we roll this die and get a number greater than 7 is 3/10. How about the probability that we get a number divisible by 4? There's still 10 elements in the sample space, so that will be the denominator. The numbers that are divisible by 4 are the 4 and the 8, so there are 2 elements, 2 numbers that are divisible by 4. So the probability that we get a number divisible by 4 is 2/10, which would simplify to 1/5. So what if we ask for the probability that we have a number greater than 7 when we roll, or a number that's divisible by 4? Well, you may think, well, let's just add those probabilities together. So 3/10 plus 2/10 is 5/10. Well, that's not quite right, because these two events, getting a number greater than 7 and getting a number greater than or divisible by 4, are not mutually exclusive events. There's some overlap in the two events. The numbers that are greater than 7 are the 8, 9, and 10. And the numbers that are divisible by 4 are the 4 and the 8. So the 8 is getting counted as both being a number greater than 7 and being a number divisible by 4. So if we add these two probabilities together, the 3/10 and the 2/10, we're actually double counting that 8. So how do we deal with that? So if we have two events, A and B, and they're not mutually exclusive events, then if we want the probability that event A or event B happens, we can certainly add together their separate probabilities, probability of A plus the probability of E, but then we have to subtract from that the probability of their intersection. In other words, we're subtracting the probability that that element that is in both sets occurs. So in this case, the 8 is in the intersection. So the probability that we get that element that's in both of those events, the number that's greater than 7 and the number divisible by 4, is 1/10, because there's one element out of the 10 that's in both sets. It's in the intersection of the two sets. So the probability that we have a number when we roll that's greater than 7 or divisible by 4 is 3/10 plus 2/10 minus 1/10, which is 4/10. And look carefully, there's only 4 numbers that are circled up there, the 4, the 8, the 9, and the 10. So the 4 in that numerator makes sense, and 4/10 will simplify to 2/5. Now, a lot of probability experiments have to do with cards. So let's think about a deck of cards. A deck of cards, a standard deck of cards, has 52 cards in it. It has 4 suits. The suits are the spades, the diamonds, the clubs, and the hearts. And it has kinds of cards. The kinds of cards would be the 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9, 10, Jack, Queen, King, and Ace. So there are 13 kinds of cards in the deck. The Jack, the Queen, and the King can be called face cards. Now obviously we also have some cards that are red, that would be the diamonds and the hearts, and we have some cards that are black, that would be the spades and the clubs. So let's say we have the standard deck of playing cards, and we want to know what's the probability that if we draw a single card from this deck, that we draw a face card. Well, there's 52 cards in the deck, and there's 12 cards that are face cards. So the probability that we have a face card and we pull a single card from this deck is 12 52nds, which simplifies to 3/13. The probability that we pull a red card from the deck, well, the denominator is still 52, but now we need to count the red cards for our numerator. There are 26 red cards, 26 divided by 52 is 1/2. How about the probability that we pull one card from the deck, and that card is a face card and a red card? Now, face card and red card means, because of the word and, that we're looking for cards that are both face cards and red cards. And that would be these 6 cards. The Jack, the Queen, and the King of diamonds, and the Jack, the Queen, the King of hearts. So there are 6 cards out of the 52 that are face cards and red cards. That probability simplifies to 326. How about if we pull a single card from the deck and we want to know the probability that that card is a face card or a red card? Now, or means it could be either a face card or a red card or a face card that happens to be red. Well, the probability that we pull a face card out is 12 50-seconds, and the probability that we pull a red card out is 26 50-seconds. But we have to be really careful when we're looking at that word or, because we have now counted some cards twice. In fact, the cards we've counted twice are the cards that are both red cards and face cards. So that would be the 6 out of the 52 cards that are the red Jack, Queen, and King. So the Jack, Queen, and King of diamonds and the Jack, Queen, and King of hearts. So we have to subtract 6 50-seconds because we've double counted those 6 cards. So the probability that we have a face card or a red card is 32 50-seconds, which simplifies to 8/13. Now let's look at something a little more complex. 2 ordinary 6-sided dice are rolled. Find the probability that the sum of the rolls is 6. Now what makes this a little more complex is we're looking at what happens when we roll 2 dice, not 1, and we're looking at what happens when we add those 2 numbers together. So let's organize the information that we need to look at for this problem. There's 2 dice, so let's call them the first die and the second die. And each of those dice can have the numbers 1 through 6 facing upward when we roll them. Now what we're interested in is the sum of the rolls. And if you look carefully, you'll notice that within this table there are 36 boxes to fill in for the 36 sums. So for example, if we roll a 1 and a 1, we're going to have a sum of 2. A 1 and a 2 would be a sum of 3. A 1 and a 3 would be a sum of 4, and so on. If we roll a 2 and a 1, that's a 2. 2 and a 2 is a 4, and so on. So we can complete this table to look at all the possible sums we can get all the way up to rolling 2 6s, which would be a sum of 12. So we have 36 possible outcomes in this experiment. That means that the denominator for our fraction, for our probability, is going to be 36. 36 being the total number of outcomes in the sample space. Now if we look at the numerator is going to have to be how many ways can we roll a 6. And if you look at the table, you'll notice that there are 5 ways that we can roll a 6. That would be getting a 5 and a 1, a 4 and a 2, a 3 and a 3, a 2 and a 4, or a 1 and a 5. So the probability that the sum of our 2 rolls is 6 is 5/36. Now we can use the same table to find lots of probabilities that occur when we roll 2 dice and we add their numbers together. For example, if we want to know the probability that the sum is greater than 11, we would have to say that out of these 36 rolls, we want to find all the possible ways that we can get something that adds up to more than 11. And there's only one way that can happen. That's to get a 12 by rolling 2 6s together. So that probability is 1 out of 36. Probability that the sum is less than 2. Well, that means out of the 36 rolls, we want to find every way that we can add these 2 numbers together and get something less than 2. And there aren't any. So the probability that we have a sum less than 2 is 0. Now, since this can't happen, we call this an impossible event. So the probability of any impossible event is always going to be 0. How about the probability that the sum is greater than 1? Well, that means out of the 36 possible rolls, we're looking for everything that has a sum greater than 1. And if you look at the smallest sum we can have, that's 2, which means every single one of these sums is bigger than 1. So all 36 of the 36 rolls are greater than 1, which means the probability that the sum is greater than 1 is equal to 1. Anytime you have a probability equal to 1, that means you have a certain event, something that must happen. So it's absolutely certain that when you roll 2 dice and you add the numbers together, you will get a sum that is greater than 1. So that's been the basics of probability. We'll look at a lot more probability problems that are somewhat more complex, but this is a good start to looking at what we need to explore some probability problems.